We as scientists have been given this incredible script.
Quantum computing and fundamental forces are at the cutting edge of modern physics, shaping the way we understand the universe. The world we inhabit is governed by invisible forces, forces that dictate the movement of galaxies, the behavior of subatomic particles, and the very fabric of reality itself. These fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, hold the universe together. Meanwhile, an entirely new paradigm of computation is emerging: quantum computing. This revolutionary technology leverages the bizarre principles of quantum mechanics to perform calculations beyond the reach of classical computers. But what happens when we examine these forces through the lens of quantum mechanics? Could quantum computing unlock secrets about the fundamental nature of reality? Each fundamental force operates at different scales and plays a unique role. Gravity, described by Einstein's general relativity, governs large celestial bodies, while electromagnetism controls everything from electricity to light. The strong nuclear force binds atomic nuclei together, preventing matter from collapsing, while the weak nuclear force governs radioactive decay. But how do these forces interact, and can quantum computing help us unify them? Gravity, the weakest yet most pervasive force, continues to puzzle physicists. General relativity provides a macroscopic explanation, describing gravity as the warping of spacetime caused by massive objects. However, this classical approach fails at quantum scales, where particles like gravitons, hypothetical quantum gravity carriers, remain elusive. Quantum computing offers a way to simulate gravitational interactions on tiny scales, potentially shedding light on the mysteries of quantum gravity. Electromagnetism governs the interaction between charged particles, leading to phenomena like electricity, magnetism, and light. Quantum electrodynamics, QED, extends this force into the quantum realm, explaining how photons mediate interactions between particles. Classical computers struggle with its complexity, but quantum computers excel at handling probabilistic and multivariable equations, offering new insights into high-energy physics. The strong nuclear force, responsible for binding protons and neutrons in an atomic nucleus, is incredibly strong yet short-ranged. It is governed by quantum chromodynamics, QCD, which describes how quarks and gluons interact. The weak force, meanwhile, enables nuclear reactions that power stars. Understanding these forces is crucial for nuclear physics and energy research. Quantum computing can simulate the intricate interactions of these particles with unprecedented accuracy, accelerating discoveries in particle physics. Quantum computing originated from the realization that classical physics couldn't fully describe the behavior of particles on quantum scales. Early pioneers like Richard Feynman and David Deutsch theorized that a computer built on quantum principles could outperform classical machines in certain tasks. This idea led to the development of quantum algorithms, such as Shor's algorithm for breaking encryption and Grover's algorithm for searching databases exponentially faster. Today, tech giants like IBM, Google, and startups like Rigetti Computing are racing to build the first fully functional quantum computers. Milestones, such as Google's claim of quantum supremacy, where a quantum computer outperformed the best classical computer, demonstrate the field's rapid progress. However, challenges like error correction, decoherence, and scaling quantum processors remain hurdles to widespread adoption. Quantum computing's true power lies in its ability to model complex systems that classical computers struggle with. Scientists are leveraging quantum algorithms to simulate high-energy physics experiments that would require billion-dollar particle accelerators. They explore quantum field theories that describe how particles and forces interact and investigate quantum gravity, potentially unifying general relativity with quantum mechanics. One promising avenue is the simulation of black hole dynamics. Black holes challenge our understanding of fundamental forces, merging gravity with quantum effects. Quantum computing could help solve paradoxes like Hawking radiation and information loss, revolutionizing our grasp of spacetime. Beyond physics, quantum computing is poised to revolutionize numerous fields. In material science, it can simulate molecular structures to design new materials with superior properties. In cryptography, it can break classical encryption methods while also enabling ultra-secure quantum encryption. In artificial intelligence, it enhances machine learning models with quantum-enhanced data processing. The synergy between quantum computing and fundamental forces is unlocking doors to unprecedented discoveries. As quantum hardware improves, we may finally crack the code of quantum gravity, unveil the nature of dark matter, and even discover new forces beyond the standard model. Quantum computing isn't just a technological marvel, it's a key to the cosmos. As we stand on the brink of a new era in physics, one question remains: how far will quantum discoveries take us in understanding the ultimate nature of reality? The intersection of quantum computing and fundamental forces provides an opportunity to push scientific boundaries beyond what was once thought possible. Researchers are increasingly turning to quantum algorithms to tackle problems previously deemed unsolvable. One such challenge is the unification of general relativity and quantum mechanics, two theories that describe reality in fundamentally different ways. While general relativity explains gravity on cosmic scales, quantum mechanics governs the behavior of particles on microscopic scales. The inability to merge these theories has been a long-standing puzzle in physics, but quantum simulations may offer a path toward bridging this gap. Quantum computers can model exotic states of matter, such as quantum foam, which is hypothesized to exist at the Planck scale where spacetime itself fluctuates. By running highly detailed quantum simulations, scientists may unlock insights into the nature of spacetime and the possible existence of hidden dimensions. Moreover, quantum gravity research could offer answers to some of the universe's biggest mysteries, including dark matter and dark energy, the unseen forces that influence cosmic expansion and galaxy formation. Quantum computing also has the potential to revolutionize particle physics by providing an alternative to large-scale experiments. Traditional methods, such as using particle accelerators like CERN's Large Hadron Collider, are costly and resource-intensive. Quantum simulations, on the other hand, could recreate high-energy collisions in a controlled computational environment. This could reveal new particles and interactions without the need for billion-dollar infrastructure. The implications of quantum computing extend far beyond theoretical physics. In chemistry, quantum simulations allow researchers to analyze molecular structures with precision never before possible. This has direct applications in drug discovery, materials science, and energy production. By simulating molecular interactions at an atomic level, scientists can design more effective pharmaceuticals. They can develop ultra-efficient batteries and create new superconducting materials that could revolutionize technology. Quantum computing's ability to handle complex optimization problems makes it a game-changer for industries such as logistics, finance, and cybersecurity. Traditional encryption methods rely on mathematical problems that would take classical computers thousands of years to solve. Quantum computers, however, can break these encryptions in mere seconds, prompting the development of quantum-resistant cryptographic protocols. Governments and private institutions are investing heavily in quantum security to protect sensitive data from future quantum-based attacks. In artificial intelligence, quantum computing enhances machine learning algorithms by enabling faster data processing and more efficient pattern recognition. This could lead to breakthroughs in AI-driven healthcare, autonomous systems, and scientific research. The ability to process vast amounts of data simultaneously opens up new possibilities for deep learning and complex simulations. It paves the way for smarter AI systems with unprecedented capabilities. As quantum computing continues to evolve, it is becoming increasingly clear that we are on the cusp of a technological revolution. The fusion of quantum computing with fundamental physics holds the potential to reshape our understanding of reality and drive innovation across multiple disciplines. While significant technical challenges remain, including error correction and hardware scalability, researchers are making rapid progress in overcoming these obstacles. The next decade is likely to witness major breakthroughs that bring quantum computing closer to practical applications. With advancements in quantum hardware, we may soon have the ability to perform calculations and simulations that were once thought impossible. The question is no longer whether quantum computing will transform science and technology, but rather how quickly and to what extent. The convergence of quantum computing and fundamental forces is not just an academic pursuit, it is a journey toward unlocking the deepest secrets of the universe. From exploring the origins of the cosmos to developing next-generation materials and medicines, the possibilities are limitless. The only certainty is that the future of quantum discovery is just beginning.